So I also would like to thank IPAM and the organizers for putting this together and for giving me the opportunity to present this work. Okay, so I'm going to talk about machine learning for fluid mechanics, and the emphasis that you will see in this talk is about for fluid mechanics, and I would like to show you at some point a personal history of my involvement with machine learning and how I have been using it and developing it for fluid mechanics problems. Before I start, I'd like to acknowledge all the PhD students. Michele and Sibyl were my first two PhD students working in machine learning actually about 25 or so years ago. And also I had the opportunity to work with some great people. Jürgen Schmidhuber from ITSIA, Kostas Papadimitriou from Thessali, and Themis Sapsis. So an outline of the presentation, as I said, I would like to give a history. In some sense, it will be a personal history, and it will be a history of machine learning from my perspective. And I would like to discuss in these terms of this history some of the early work that has been happening on neural networks and aerodynamics at NASA Ames, and I'm talking about the early 90s. I would like to discuss some more interfaces between machine learning and fluid mechanics. I'll show you Lighthill's report and what it did to fluid mechanics, to machine learning. Perhaps people in machine learning don't know who Lighthill is. I presume fluid mechanicians do. I'll show something about Reichenberg's Galton breadth, and then for the things that I have been doing, I will discuss learning for fluids in terms of dimensionality reduction and prediction optimization, and then conclude with sensing. I'll start actually with reinforcement learning for flow control, and then hopefully I will discuss Bayesian experimental design for sensing. So just to start, this has been my motivation for getting into this field. I don't know if we get the sound, but who you see here is an Israeli pilot who, back in 1982, he was able to land an aircraft with only one wing. There was a mid-air collision, and then he lost his wing, and then he was able, by using all sorts of tricks and things like that, to land an actual F-15 with just one wing. So this is 1983, and at the time, 1992, I moved to the center. 1994, I moved to the Center for Turbulence Research at NASA Ames. And at that time, there was a computational sciences division that was led by Chuck Jorgensen. And at that time, people had started to look into self-repair in flight control systems. And they had been starting to look into how can you get actually a neural net to operate on the controller of the aircraft and try to have actually the capability of equip aircraft with the possibility of landing themselves, even if you don't have such a fantastic pilot like the Israeli pilot that you just saw a minute ago. So some of the projects that they had was to use neural nets for adaptive aircraft control, and then they had some elementary neural networks. And then what you see here is that they were using neural nets to learn the plant that they had. They had a virtual aircraft that they had all sorts of equations, and then they were using some very simple aircraft and some very simple neural nets, and then the neural nets were able actually to capture all the behavior that the plant will give them. My actual involvement with these things when I started going to there was actually starting to do and to use neural nets to interpolate data from wind tunnel experiments. What you see over here, this is the NASA Ames wind tunnel. So they will put inside their aircraft like this one. This is the Shark, one of the dark projects, and the height of this wind tunnel is about 100 meters, and then it was kind of expensive to do all sorts of experiments for the different angles of attack for this aircraft, and then instead of doing experiments, the idea is, can we use neural nets in order to interpolate between experimental values and to try to predict the response of the aircraft. So I was playing with some of these things and then reading also papers. I had the opportunity at that time to go to the Department of Psychology and go and take a course by David Rumelhart, who at that time was teaching backpropagation. In fact, actually, I remember at that time looking at backpropagation and thinking this is nothing but the chain rule of differentiation, and backpropagation was what was happening to my career. But it was a fascinating time to get into neuroscience and to understand how neurons work and try to. Basically, I was not having a concrete thing, how do you take all these things and put them in fluid mechanics, but slowly starting to understand and play around with these concepts. So one thing that became kind of evident at that time, there was in fluid mechanics, the key concept was for dimensionality reduction was something called the proper orthogonal decomposition. The idea of the proper orthogonal decomposition is that you take data, you form the covariance matrix, and then you have to find your favorite eigenvalue, eigenvector solver, and try to identify the dominant eigenvectors. And at the same time, by reading some of these books back then, you realize that there is another concept, that you don't have to form a matrix, but instead, what you can do is you can employ a module, like a neuron that we have here, where you have the input, you pass it through some kind of a function, and then you produce the output, and then the idea is that you have to get some data and then try to minimize this least squares function over there and identify what are the parameters of the network. You could have all sorts of different activation functions, and then there was a very interesting thing, at least for me at that time, to realize that you could have just simple linear neural networks, and then you could show that there was an equivalence between the proper orthogonal decomposition and linear principal component analysis. Now you have to understand that these days everything may seem to be obvious to the fluid mechanics community, that they have to do things like that, but at that time, whenever you talked anything else but POD, you were considered to be something like a heretic, or at least to put it mildly. So my idea, or what I wanted to do, was actually to do control of turbulent flows like this one. What you see here is the flow over a channel. You see the cross-section of the channel, and then what you see is you see fast fluid, which is the red stuff that you see here, and low velocity fluid that is ejected from the wall. And what we want to do is we want to apply control by blowing and suction at the wall and to try to eliminate these particular structures of streaks that you see on the wall of a turbulent flow. So fascinated by neural nets, I bought myself a book. And then there was even software that came in a disk. And then you have to appreciate this was required 1 megabyte of RAM for this to run. And this is 1992. And this is some of the places, at least myself, I learned how to program and play with neural nets. Then indeed, we programmed this thing. And actually, I have to tell you that it took this paper that appeared about 4 years in order to appear in the Journal of Computational Physics, because people will say, so what? I mean, who cares if now instead of just doing it with a POD, you can do it with neural nets. And what you see is reconstruction by using the same amount of modes for a certain part of the velocity field colored by some kind of vorticity magnitude. This was reconstruction by the POD. This was reconstruction by the nonlinear neural nets. And in fact, at that time, out of desperation, in the beginning, we put one layer, we made it nonlinear, it didn't work, and then we found, just by accident, that if we put a second layer and a third layer, these things were working. So we were just empirically playing around and actually ended up having, let's say, a deep neural net back at that time that seemed to be working very, very well. We did other things. The other thing is, as I said, I was interested very much in control. So when you try to do control, one of the things that we were interested is it possible to reconstruct the flow above the wall by using information only at the wall? So one of the failures of neural nets at the time is if you could collect pressure and shear stress sensors, it was not possible to recover the mean velocity profile above the wall. But then if you look at the equations of fluid mechanics, then you can see that if you do a Taylor series expansion of the velocity field just above the wall, if you have the shear and if you have actually the pressure gradient on the wall, this is an expansion in terms of the for the velocity field in terms of vorticity and vorticity flux. And then the only thing that we asked the neural net to do was to take the rest of the stuff that this exact expression will not get. And indeed, we were able to get some very good agreement between the reconstruction made by the neural net and the direct numerical simulations that we had at the time. We didn't use the neural nets for control. I will come back to that why. But at the same time, we were using different ideas of control that I'll talk about to do simulations and control of jets. And again, it was impossible, at least for me, to publish anything in any fluid mechanics journal. They will be dumped away right away. Dumped out right away. So all this work has appeared in a Center for Turbulent Research research briefs. Another thing that we did is, at that time, I was also talking to biologists, and we started to play around with some of the first support vector machines, hidden Markov models, etc. And I know about this time also there was this work by Jan LeCun that was showing that you can get neural nets to outperform humans in the digit recognition. Well, the task here was to actually, I didn't know of the work of Jan LeCun, I just found out later. I had met Julie Theriot, who is a biophysicist at Stanford. And then what Julie has shown me is that you can have different cells called ceratocytes. And depending on what temperature these ceratocytes are finding themselves, they have different trajectories. And the question is, how can you train a neural net to, or all these different machine learning algorithms to do classification of the trajectories and to identify in which temperature they belong. And actually, we found some very interesting results. And in fact, we found that neural nets could outperform Julie, who had been doing experiments of that kind all her life. So another thing that I was playing with at the time, another person that was at Stanford at that time, which I had a great opportunity to attend courses from, was John McCarthy. And it was the ideas about artificial intelligence. And there was one particular thing that I liked, which is kind of goes against the dogma of what we have in fluid mechanics. So I will explain. So according to John McCarthy, intelligence is the computational part of the ability to achieve goals in the world. And the interesting thing is this concept over here, is that you want to understand or predict or control a particular system in terms of its outcomes rather than its mechanisms. And the classical dogma in fluid mechanics is we first understand, and then after we understand, we can go and do something and try to control because we have understood what is it that we want to control. And the thing that is surprising, or the thing that I would like to show you, is that this dogma does not necessarily always hold, because in fluid mechanics, as soon as you control a particular system, you may end up being in another physical regime, which is completely different in physics than the regime you started with. So everything that you can study in an uncontrolled fashion, unless you trigger some kind of instability or anything like that, sometimes it's more important to care about outcomes and then study mechanisms. So another thing happening at that time was people also were starting to think about airplanes that may go to Mars. So there was the idea of having smart wings. And what are smart wings? Smart wings are wings that they will be able to change their shape. Because the idea is that if you can do any kind of wind tunnel experiment down here on Earth, but what if the environment in Mars is completely different than what you do the experiments on down here? So the idea is that you could have an onboard controller and some kind of a foam core, and then this wing will change in its shape in different ways. So I tried to play at that time and try to see whether it would be possible that you can do fluid mechanics control without knowing any fluid mechanics whatsoever. So is it possible to do control and to do something without knowing any fluid mechanics? So this is a flow past the cylinder. This is the vorticity. So what we did at that time is we put a whole bunch of actuators on the surface of the cylinder. These actuators could move tangentially on their surface, and they could have positive or negative velocity. And then this is a 16-parameter vector that we had. And then at that time, we used genetic algorithms to try to see if we can minimize the drag. Indeed, we found spectacular drag reduction of about 60% behind these cylinders. And the interesting thing was that to look after that at what was the probability distribution, or the histograms, if you like, of the actuations in good solutions of this parameter space of the genetic algorithms. So we had a metric, and the metric that we introduced was the first moment of this histogram. So whenever we found that there will be, so you have to understand that for every one of the solution vectors, you will get one value from each one of these blocks, and that would be your actual actuation, and this shows you statistics of the good solutions. So for example, for actuator number 7, you could get in the good solution vector anything positive or negative, which basically implied that actuator number 7 over here is not really interesting. And then when we did the metrics of the momentum of the first moment of this probability distribution, we found that the interesting actuators were actually actuator 3 and 4, which is interestingly close to the separation points, and 13 and 14. So you don't know any fluid mechanics. You play around. You find out that something is happening to your actuators, and they give you good solutions. So you might as well eliminate the rest of all the other actuators and try to do an optimization using only these 4 actuators so that it is energetically much better. Now these histograms become sharper, and the drag, it's becoming less than the drag that we had before, but not by much. We played further with this. We could do it also in 3-dimensional cylinders, and as a proof of concept also of what you can get, which is kind of unexpected, we found out that you can have a 3-dimensional flow behind the cylinder, and by properly rotating, properly were values that came out from an evolutionary algorithm, you could actually 2-dimensionalize the flow and get actually significant drag reduction. Now, so going away from more and more away from neural nets and into all this optimizing and controlling, another thing that I was doing at that time is I was trying to understand the physics of the flow, and I was understanding that these shear stresses that you have here, they're signatures of vorticity. So what I did at that time is about taking something which is the Light-Hill's mechanism for vorticity generation and formulate it into a linear control problem where you basically can say what is your target vorticity flux that you want to have on the wall. You can get measurements on the wall. What is your vorticity flux? And then this is a matrix that tells you that if you blow or move or do anything on the wall, this is how much you're affecting your vorticity. And then by applying that, I found that you could actually get from this pattern to something with rollers happening on the near wall region of the turbulent channel. And then this was no control, and this was control. So understanding physics was actually a very useful thing. So for those of you who don't know Light-Hill, maybe you know Light-Hill through, is there sound from here that's coming out or not? Can I have the sound for this, please? So how many of you know about the Light-Hill report? Okay.
What's that?
And how many, sound for my video now, yeah. And how many of you know Light-Hill in general in fluid mechanics? Okay, so the set is not coinciding, which is good. I don't have that. I think I don't have that. Oh, I have that.
Good.
Okay. Now what?
Now it should play. Can you turn it up more in here?
Community has a heavy responsibility
Okay.
to put forward its carefully is with the overselling of the longer-term future of computers. The scientific community has a heavy responsibility to put forward its carefully considered view of the facts to avoid the public being seriously misled.
So the Lighthill report was at the time, John McCarthy is sitting actually somewhere here. You can see if you see this video on YouTube. The Lighthill report was happened back in the 1970s, and that was when the Royal Society had put together a committee to understand what is the impact of artificial intelligence. And then Lighthill led a scathing report against artificial intelligence with all sorts of different arguments. And one of the arguments was actually that artificial intelligence has failed blatantly in speech recognition, and you see the irony that his talk is automatically transcribed over here. Of course, another thing was that there is this animosity between different communities, and there is a position here about Lighthill. Like, who was Lighthill? After all, he was a researcher in fluid dynamics and aeroacoustics, where it's easy to be misled by complicated differential equations involving continuous variables. You see, this is written by computer scientists, and where non-existent solutions arise so often. So there is this thing between the two communities. But again, Lighthill was saying that computers are not worthy of anything, and indeed, actually, I took this plot where it shows you what is the power of computers. So this is back in 1999 when I was doing my work in machine learning, to arrive in today where we have this review paper with Stephen. Whatever it would have taken us a year to solve in 1999, we can do it today in 5 minutes. And that's a big game changer. It's a big game changer because you can think completely different. So at that time, I was led to abandon everything about neural nets, etc. And I think it's this power of computers is something very, very important. So back to what I wanted to say is I want to say a few things also about another line of work in artificial intelligence that was happening in Berlin at the Hermann Pfottiger Institute. Again, it was an experimental work led by Ingo Rechenberg. And what Ingo Rechenberg was trying to do is he was trying to see whether he could find an optimum aerodynamic shape. So according to what you may know in fluid mechanics, the flat plate has the minimum drag coefficient. So he would create a corrugated device. This is all experiments. At that time, it was difficult to get random numbers. So he will use something which is the Galdon bread, which has sticks coming out. He would assign a ball to each one of these angles over here, let the ball fall down, and then accordingly let the angle change. Now you can formulate all these things as some kind of a variation of your parameter space based on some kind of a probability distribution. At the time, this probability distribution was just a diagonal matrix. Here I have put a covariance, as I will show you later. But the interesting thing was that he didn't allow this thing to be only a random search. As he was getting away or closer from the minima, he was kind of adapting this thing, this covariance matrix. He was kind of learning, if you like. And the interesting thing is that his final design is actually not a flat plate. And we have done simulations where we show, indeed, you can have corrugated plates that have less drag than a flat plate. The evolution of this was actually thanks to Nico Hansen. Nico Hansen was a PhD student of Ingo Rechenberg. Nico Hansen is a special individual. He was a medical doctor that decided to abandon medicine and go and do a PhD in mathematics. He worked for Ingo Rechenberg, and then he started together with Ostermeyer to develop a technique called covariance matrix adaptation. So the idea of the covariance matrix adaptation is that you have a covariance matrix, And then this covariance matrix is evolved as you proceed. So what you do is you have a fitness function, and then what you do is you discard the low fitness function data, and then you're using the new better data in order to construct a covariance matrix. And when Nico came to our lab, covariance matrix adaptation was up to here, because basically they were creating covariance matrix only by using the mean of this data. And I thought that why waste all this other data that you have? So the idea that we had in our lab was that you can actually extend this covariance matrix to have also covariances between all the members between different generations. So this is the rank 1 update was happening only by using the mean of this data, and the rank new update involves all the good points between different generations. All these stochastic optimization techniques were very good for black box problems. And another thing that was actually interesting to do at the time, so in a sense, what you're trying to do is you try to create a model to discover what is the probability distribution of good points. And at the same time, because we were doing expensive function evaluations, we were using things like Gaussian processes and other techniques in machine learning in order to create meta models to replace expensive evaluations in the selection process. So there was a two-way where you can do in learning to learn from data, meta models for the expensive simulations, and using some kind of learning to learn the probability distribution of good points. I'd like to show you one example of the things that we have done. We did a whole bunch of different things. One of the things that I liked very much is that very often we hear that in nature is optimal, everything is perfect in nature. So we said, okay, let's see what is the optimality of nature. So what we did is we tried to specify an objective. In this particular case, it was going to be escape distance, that a particular animal tries to escape from a disturbance. And we didn't specify how these animals should be moving, but we wanted to discover it by specifying an objective function and then using evolutionary algorithms. So the problem is like this. You see that these larvae, they have actually encoded in their nervous system that they bend in a particular shape, which is this shape, and then they have a particular program in the way that they are escaping. And people have tried to understand this in terms of vorticity, etc. There has never been a simulation doing that. So we did simulations, and we found actually the C-start to be the outcome of the optimization. And I want you to pay attention that all these things are the amount of numbers of direct numerical simulations that we were doing in order to arrive to this particular solution. So having fast codes is very, very important. And what we found is by using Lagrangian coherent structures is we found that actually what these guys do is they trap fluid in their near body, and then as they are creating a vortex is taking all this ball of fluid inside it and transports it away. So these little guys, the way they escape so fast is not because they have a strong tail, but because they are very clever fluid mechanicians. They are trapping a ball of fluid, and they use vorticity to take this ball of fluid away. So it's like you're on a boat, and you throw away a stone that you have with you, and then you are able to escape. Moving on, other adventures in machine learning and fluid mechanics that I'd like to mention is the idea of learning to predict. This story also goes to when I went to Switzerland in 1997. I had the good chance of meeting Jürgen Schmidhuber. And Jürgen Schmidhuber is the person who developed long short-term memory networks. The idea at the time, I started to play with recurrent neural networks in order to do time-dependent problems that we often have in fluid mechanics. I visited ITSIA, and then Jürgen showed me the long short-term memory networks, which many of you probably know today is the workhorse in many examples in science. We wrote actually a proposal together to the Swiss National Science Foundation. The Swiss National Science Foundation you get actually a success rate of maybe 50 or 70%. I think from all my proposals, this is the only one that got rejected. So this is back in 1997. They rejected fluid mechanics and long short-term memory altogether. In any case, we continued with Jürgen doing all sorts of things in fluid mechanics, but I want to show you some work that we have been doing with Themis Subsys actually in using recurrent neural nets along short-term memory networks in order to predict fluid flows. So the idea is that you want to use some kind of a reduced order model in order to predict the dynamics of a system. And the basis for all these predictions are something which is called Takens theorem, that says that you can reconstruct the dynamics of the system, maybe not by having all the degrees of freedom available to you at all times, but maybe looking at only 1 degree of freedom and then collecting time delays of this 1 degree of freedom. So what we did is we tested how good are the recurrent neural networks with long short-term memory on something which is called the Kuramoto-Sivacinski. So we take the Kuramoto-Sivacinski equation. We have one parameter here that I want you to pay attention, is the hyperviscosity of this particular term. And then we did not train the recurrent neural nets on the full information, but we were not able to get it to work actually, but instead we did some proper orthogonal decomposition and tried to train the recurrent neural net on the dominant modes of the flow. So just to give you an idea, this is the high dimensional or the full states space. Then this is the training data that we had. And then we use a recurrent neural net in order to predict. So the recurrent neural nets you receive is different than the classical neural nets in the sense that you have input-output data. The input and output data are time series. And by doing the connection of the neural net, you are respecting the time series connectivity. If you had the fully connected neural net, perhaps this input over here would have been connected with this output over there, which would have broken down this sequential, this sequence of time signals that you had. So here is where the places that we trained, and then I want to show you how far out it was able to predict, or where was it actually failing. So the yellow is this is after the training. So we have been training on the modes, not on the full state information. Then we're able to predict the modes up there in the red line. It's doing a pretty good job up to the pink line, and then the orange line you start to see that it starts to fail. So this is the forecasting error that we had. After we have the modes, then we can do zero padding and recover the full state space information. And then this is the errors that we get in the full state space. And this is the errors that we get on the modes for this particular recurrent neural nets. The problem was that if you take this new and make it even smaller, actually recurrent neural nets with LSTM were terrible, and they fail. And I want to stress this thing because we found that everybody says you can predict everything, you can predict chaotic systems, etc. And our experience is that you cannot actually predict chaotic systems with recurrent neural nets. It's a long story, but there was at some point this article that appeared where we are even quoted as saying that we predicted chaos, even though in our paper we said, no, we don't predict chaos. So we actually said that we fail in predicting chaotic systems. Nevertheless, this is what you get on the web. So we are using, now the reason I'm presenting these recurrent neural nets, because they are very important for another thing, which is the last part that I would like to show you. So the last part that I'd like to show you is how to do learning for control. And what do I mean by learning for control? We are interested in fish swimming. And we have been interested very much in fish schooling, but even in this particular case where you have only these two fish, we're interested of how this guy how this guy is following this guy. Is it only because of visual cues, or there is some kind of a hydrodynamic benefit of being on the wake of another guy? And there is this paper that has appeared that says that indeed if fish are swimming in a diamond configuration, then because of the way the vortices are coming, then these guys back here, they have less drag. There is a big problem with this picture. The big problem with this picture is that the fish are glued on their positions and they're moving. If you let this thing go in a simulation, as I will show you, then what happens to this fish is they will be actually moving and changing shape. We're using vortex methods with wavelet adapted grids to do all these kind of simulations. Again, having fast simulations is very, very important, and doing simulations of this kind with multiple bodies, I think is quite a challenging enterprise. So this story of how do you go about controlling? So we tried optimization. Optimization doesn't work. And there is another place where AI and artificial fish have been used. So this is work by Dimitri Terzopoulos, where people have been using learning algorithms, some kind of early form of reinforcement learning to make fish avoid obstacles, etc. So what was pioneering and interesting about this work is that they could get their models to learn to behave and to look like they're swimming like real fish. The only complaint that I have about that is there is no fluid mechanics there. They just had some kind of an ordinary differential equation model for the fluid mechanics. So what we wanted to do was actually to repeat some things like that, except that now we're going to be doing direct numerical simulations for the fluid dynamics. So these are very expensive simulations that they will be combined with reinforcement learning. So what is reinforcement learning? In brief, you have some kind of an environment, and then you're observing something in your environment. In our particular case, we may be observing fish, and then you have a state, and then you will give the state into this brain over here. I'll tell you in a second what this brain is, and then this brain will produce some kind of a stochastic action. The action actually would affect the state of the environment, and you will get some response back from the internal environment in terms of a reward. Okay? So now I will not get into all the details of reinforcement learning, but I want to tell you that we are using parametrized policies, and we are using parametrized policies in particularly for partially observable Markov decision processes. We don't have access to the full state of the system. We cannot do the same thing as people who do computer games do. So we're giving to our network some kind of a state, and then we're getting out some kind of a mean and a variance for this policy. The policy tells you if you are in this state, what is the action you should be taking in order to maximize your long-term reward. Another nice thing about using a neural net to do the policy, the parametrized policy, as you will see in a second, the way we update the policy is by using stochastic gradient descent, and having an analytical expression over which to take gradients over the policy is very important. So again, reinforcement learning and deep reinforcement learning has been used all over the place, has made a lot of news, and I want to tell you again that here, this is a simple case for us in the sense that here you have full observation, you know every pixel, and every kind of iteration that you do may take milliseconds. When you do direct numerical simulations of multiple swimmers, this may take hours or weeks to simulate. So it's important to appreciate that, yes, people have done it for that, but it's not automatic that you can do it in fluid mechanics. So very briefly, to tell you what we have contributed in fluid mechanics, this is something which is called the value function. And here is the rewards that you take in every time that you're playing the game. These are the actions that you take. And here is the state that you get. This can be an equal sign in case this is a deterministic. This is the state that you arrive by being in a state before and then making a certain action. And then what you try to do is you try to maximize the value function. And then you can see that this is a recursive relationship. So you ended up having this Bellman equation, which is the same equation that you have in dynamic programming, except that in our case, these transitions that you have from state to state is not really a closed model, because the state to state, actually the choice of the states is a very, very important decision that we have to make. And there's another function that I will try to show you, which is the state action function, which in this particular case tells you what is the combination of the value action function, and if you are in a certain state and you take a particular action and you take a Bellman equation. And just as an anecdote again, we submitted a paper of one of the works that I'll show you to a fluid mechanics journal, and then we had written in the paper the celebrated Bellman equation, and the reviewer, one of the reviewers, among the many comments that he made to reject the paper, he said the Bellman equation may be celebrated in artificial intelligence, but not in fluid mechanics. And I hope that this will be something that will eventually change. So an algorithm, just to get an idea of how you go about doing things. So you initialize in Q-learning, and usually here you have the states and actions in a table, not necessarily in a parametrized form. And then you can use an E-greedy policy to choose from all the different actions that you have available. You move to a new state because you did an action and you receive a certain reward from your environment, and then you do this very simple update. Again, these tabulated things have problems. So we move to parametrized policies, and in this particular case, we may have a recurrent neural net to tell us that if you have a particular state, what is the mean and the variance that you have to plug into this parametrized policy in order to act. So people have been doing these parametrized policies in the last 5 or 10 years in this community, and so the main thing that you have to say, okay, let's say I initialize my weights and I play all these different games. The question is, how should I change my weights? So what people do is they define a cost function that goes in terms of the weights. This cost function, again, is looking into the rewards that you get, and then you try to find the W's that maximize this long-term reward. So now they're using a stochastic, they have been using a stochastic gradient descent in order to update the weight. So the question is, what is this G of W? And then people propose that this G of W should be the gradient of this function. And then there is this policy gradient theorem, which is 7-year-old, where people found that an approximation of this particular gradient is given by expression of this form, where you have the parametrized policy and you have the gradient and so on and so forth. And so the key question is that you have a policy that you are updating online as you go, and you proceed and you're updating your policy. But as you're updating your policy, you're creating something that we call experiences. What is an experience? An experience is that you followed a particular policy, you received rewards, you had states, and these were your actions. So now the idea is that all these past experiences that you have developed, can you use them in order to improve the policy that you have been developing? And what people have been proposing, how to use off policy, so all the early experiences that you have, how you can use them at a later time. They propose to use importance sampling. So in this particular case, let's say this is some old behavioral policy that you had identified, and this is your new policy. So what people said, okay, let's do the sampling according to some kind of a weight, so that this weight between the current policy and the previous policy can come into the picture. And so what we proposed is that this is fine, but then people have been using this throughout the state action space. But then what we proposed is that actually once this number exceeds certain thresholds, maybe what you're comparing is you're comparing policies that are completely different than the policy that you are having right now. So this needs to be rejected. So this is off-policy actor critic. This is what people have been doing before. And this is where the old policy and the new policy are coming together through this ratio. And what we proposed in addition is to formulate a Kullback-Leibler divergence between old policies and new policies, and then to augment existing algorithms with this kind of thresholding, that first of all you do rejection sampling, but only for a certain region of this ratio over here, and if this ratio is exceeding certain thresholds, then you follow only our own way, which involves the gradient of the Kullback-Leibler divergence between old policies and the policy that you develop right now. So again, this is what people have been doing. This is the new thing that appeared in ICML 19. So we reject samples outside the trust region, and we penalize policy, or we accept all the experiences only if they are close to new experiences. So how good it is? So you will be surprised that actually we outperform everything that Google and others have done, and I hope this is recorded so people can come back to us. So these are the OpenAI gym, and this is the cumulative reward that you can get from this DD deterministic policy gradient and prioritized experience replay. And we have, I'll show you in a second results on things like that, and I will show you results in fluid mechanics problems. So what does it look like? So if you do this trust region policy optimization, you get things like the ant. So this is how their ant is working, and this is how our ant is working. And the interesting thing is the humanoid. This is their humanoid. This is our humanoid. And you measure competition by looking at this cumulative reward. And then this is the factor that it's the one parameter that our algorithm has. The interesting thing that comes out here is that this guy, based on the dynamics you have, moves very fast because one leg, as it comes forward, kicks the other leg. And that apparently does a big difference on the humanoid control. So we have taken this into all sorts of different problems. I would like to show you some of them. So we have been looking into agents in unsteady flows. So again, so what I have here is I have a Kalman vortex field behind a flow, and what I'm interested in is what if I put an ellipsoid behind? Can this ellipsoid harness energy that's coming out from the vortices of this flow? And then what we find is that indeed we are able to get some very interesting behaviors that I think we would not have a possibility to get otherwise through using this remember and forget experience replay. And this guy is being pushed away by the flow, has its own propulsion, but in general he's using much less force than if it was alone. So he's using the vortices that he has there. Another thing is that people have observed in experiments, or they have seen that trouts, very often they stay behind rocks and they're keeping their position here. So we repeated this experiment using deep reinforcement learning for a fish-like body, where now we have a swimmer, and the swimmer actually has much less, 45% less, uses much less power than if this swimmer was just in front of the cylinder and was not exposed to the vortices. So it's kind of counterintuitive, but on the other hand, you find out that doing clever things in how you use the vortices and synchronizing your motion with the shedding frequency of the bodies, you can increase your speed. you can increase your efficiency. Last example, I will put two swimmers now. This is towards doing these schooling things that we wanted to do. We can increase or decrease the curvature, and here we have only visual observation. I will not have time to tell you how now we are using Bayesian experimental design in order to do pressure and shear sensing on the surface of the body to do schooling. And then we're going to have two rewards. One reward is that you're going to have to be at a certain line behind the swimmer, and the other one is that you will have to be swimming efficiently. So the first thing that we ask the fish is that you have to minimize the distance from the center line of this guy. And this was a task that the fish there was able to learn. And we said, fine, this is interesting. But then we looked at the power that this fish was using, and we found that the power of deformation decreases. So this guy uses less power to swim than this particular guy, once it has learned to follow in this particular direction. So we found that it is indeed efficient, and we had an efficiency of 11.8%. And then we asked, okay, now maximize your efficiency, and we didn't tell him where to swim. So he had very well the option to swim left and right or anywhere, but what the optimal swimmer does is he goes actually, he, she, I don't know what it is, goes and swims back here. And the interesting thing is that you see that there is a beautiful ballet of how this guy bends his body up and down in anticipation of the vortices that are coming. And then this was actually increasing efficiency by 28%. Now, if you want to go from 2D to 3D to do reinforcement learning, forget it. We need at least another 5-10 years or quantum computing to be able to afford all the simulations that we will need to do reinforcement learning in 3D. So we said, okay, let's do what we learned from 2D in 3D. So what we did is we put this guy right in the center line behind the other guy. So now what do you think? Do you think that the second guy has better drag, has less drag, or is it more efficient than the guy in front? Why not?
You wouldn't be asking.
Huh?
You wouldn't be asking.
No, this is not a scientific argument, right? So it does not, and it's basically because if you look at it in 3D, in 2D, because it is 2D, all the vorticity is exactly behind the center line of the fish. And in 3D, the vortices go on the side like vortex rings. So this guy basically in 3D is swimming in a dead region the same way as this guy. So nothing really happens, but this guy is swimming in vortices. So you have to swim in vortices. So this is something we did. Is fine. Reinforcement learning does something, but then what can we learn from these smart swimmers? And then what we found is we created a metric between the velocity of the flow field and the velocity that the head should have, and we found that there is certain peaks. So if you respect these particular peaks, then you're supposed to get some very efficient swimmers. So indeed, what we do now is we use a PID controller, and we tell this guy, you have to swim right here, because that's where you expect that these vortices are going to be coming by observing what has happened in two-dimensional simulations. And now, indeed, we get very efficient control. I will not get into details. We actually can put two swimmers behind, each one of them taking advantage of vortex rings that you see here. And finally, this is, again, I want to stress that this is direct numerical simulation, Reynolds number 5,000, using 3 self-propelled bodies. And on top of that, we have used results from reinforcement learning to get some very efficient swimmers. So even though it seems that it's swimming in a very complex and chaotic flow, this guy has about 20% efficiency over the fish in front. I think I would like to stop here. I would like to say a few things. As far as I have seen, at least from my experiences from fluid mechanics, is that there is no universal machine learning algorithm. And that learning, as far as humans are concerned, implies finding an algorithm, not necessarily a machine learning algorithm, that is effective for the problem to be solved. And this is, I have to admit, an engineer's point of view, that I would like to solve a problem. I'd like to minimize the drag, do different things. And I don't care what is the particular algorithm that I will be developing. Another thing that I would like to stress is that is something that comes from someone from UCLA. It's from the Book of Why by Judea Pearl, who believes that machine learning is actually about creating associations, and it's about seeing and observing. And that there is better or more interesting things that one can do as we move up this ladder. There is ideas of how to do things and intervene in the flows in order to understand how things are behaving. And there is great hope for humanity, according to Judea, because things like imagining, retrospection, and understanding may not be something that is accessible to artificial intelligence anytime soon. So I'd like to close with that and be happy to take any questions you may have.